So let's give this average rate of change problem some scientific context. So it's now, we're thinking of this as a plot of the time that we've been flying a plane versus the altitude of that plane in thousands of feet. And we've chosen two different time values here. So t equals 0.9 seconds, or minutes rather, and t equals 2.7 minutes. And I'd like to know, first of all, what is the average rate of change on this interval? And second of all, what does that average rate of change mean if I'm a passenger or if I'm a pilot or something on this plane? So first of all, what is the average rate of change? How do we find it? Divide the rise by the run. And to find the run is the easy one. We just need to subtract the two t values. In other words, the run is the difference in the horizontal direction between these 2 points. 2.7 minus 0.9, that's 1.8. Then for the rise, we just need to find the y-coordinates of these points. So f of 0.9. So 12 times 0.9 minus 0.9 cubed. 10.071. Is that what you get for f of 0.9? Or again, the function we're using here to relate t and h is this function up here. And then for our second point, its y value will be given by f of 2.7. And then the rise is just the difference between those two values. And that difference is 2.646. So 12.717 minus 10.071. That's 2.646. And then dividing those two, finding the slope of that line segment that's being sketched up there, we get approximately 1.47. Okay, but now I want to know what that number, the average rate of change, which is also the slope of this line segment, 1.47. I want to know what that means within the context of this, if I'm a passenger, if I'm a pilot, or an air traffic controller, or something. First of all, what units is that slope going to have? Where do the units of a slope come from? The units of x and y. Done, what do we do with them to get the units for the slope?
So just kind of plug them in, right?
Plug them into what? So I take the units of y, which come from the rise, that this rise over here is a distance in the y direction, and so its units are the same as the units of y. And then the units of x belong to the run down here. And so the units for my slope end up being units of y divided by units of x. 1.47 thousand feet per minute. Because after all, the rise and the run had a meaning of their own, right? That we rose by 2.646 thousand feet over a period of time that measures 1.8 minutes. That's what the rise and the run meant in this instance. And so once we've divided those two together, our rate also had its units divide. So what we might say is that over this period of time, in other words, the period of time between 0.9 minutes and 2.7 minutes, our altitude, our height here, was changing at a rate of 1.47 thousand feet per minute. So it just tells us how quickly, in this example, we were rising, ascending, or descending in our plane. What's interesting, of course, is that that doesn't tell the whole story of what I was experiencing as a passenger over that 1.8 minutes worth of time. Because for a while, at least, the plane was rising. But then after a certain point, the plane stopped rising and began descending. That's why we call this an average rate of change, is it doesn't tell us exactly what's going on at every moment in time. It only tells us on the whole. When we just look at the starting point and the ending point, what was the net change? What was the net rate of change over that length of time in this example? So what we ultimately want to get to is a way to conceive the change at every single moment in time. So I know at any given time instance, is the plane going up or is the plane going down? Something like that. And that's what we're going to get to. But in order to do that, we're going to need to figure out a way to measure the slope, not just between 2 points, not even between 2 points that are maybe 1 unit apart, not even between 2 points that are 0.1 units apart or 0.01 units apart, or even 0.001 units apart. We'd like to figure out what happens to those rates of change as the spacing between the 2 points shrinks and shrinks and shrinks. And what we're going to get then is not a line that connects 2 different points on this graph, but a line that seems to touch this graph only in a single point. How are we going to find the slope of that line if we don't have 2 different points between which to measure the rate of change? So this line is something we're going to talk about in more depth tomorrow. It's called a tangent line. Tangent used in not the trigonometry sense, but in a new sense. That just means it's a line that touches the graph in one point and which goes in the same direction as the graph at that point.